Turning to slide 22, we'll look at another data set from the National Longitudinal Study of Youth 79, NLSY 79, where again we'll look at depression and self-esteem. And this is again data taken from the Ort et al. Article, and it concerns adolescents and young adults. Total sample size 8,000 plus, and total number of time points is 11. These are measured 2 years apart from 1994 to 2014. However, we don't have 11 time points for any one person. The maximum is more like 7 and a smattering of people with 8 time points. So there's a lot of missing data, perhaps some of it by design, I'm not sure. So with this large amount of missing data, you will have to use analysis option coverage equals 0 to get past Mplus default of stopping you at coverage lower than 0.10. And you have to use many starts, 20, 50, and maybe even 100. But at the same time, be aware that when you have this much missing data, model assumptions, as it says, are given too much weight relative to data. And the coverage is especially poor for self-esteem, the 11 variables designated by or denoted Y here. And you have these off-diagonal 0 coverage, so nobody has information on both the 3rd and the 4th time point. Nobody on the 4th and the 5th time point. And even worse here, 3 zeros in a row. Now it is possible to estimate, these off-diagonal elements particularly influence the estimation of autoregressive features. 3 on, or 4 on, 5 on 4, and 4 on 3. You have to borrow information further away at lag 2 to be able to infer what the lag 1 estimates would be here. And that gets too difficult for the optimization machinery when you have 3 zeros in a row here. Here we have only 2. For depression, the missing data situation is a little bit better for some reason, and we're able to do analyses of depression, univariate, without imposing invariance across time. Now, I should mention that that is one way of getting past this. If you hold autoregressions invariant across time, then you have a more stable estimation, because then you borrow from the off-diagonal elements that are not 0. And that's actually how the Ort article gets by this problem when they do a bivariate analysis of self-esteem with depression. Turning then to the univariate analysis results, we look at the AR1 model, which is the model that Ort settled on, although with the assumption of invariance, a stricter model. So you see there that we have a fairly poor chi-square. Here, to some extent, since you have over 8,000 individuals, you may blame that on chi-square becoming oversensitive with large N, although at a certain time point you don't have all 8,000. I haven't looked at the details of how many observations you have per time point in this case. Probably far less than 8,200. But anyway, for these data, you may want to also rely more heavily on RMSEA, the approximate fit. But even by that measure, probability p-value is 0 that you have an RMSEA less than 0.05, which is desirable. And even the CFI is poor. AR2 seems to work a lot better. You get a strong improvement in the log likelihood, and look at the chi-square. It drops down quite a lot. And now you have an acceptable RMSEA with p-value of 1 here. Now, ARMA 1.1 then is a model that I boldfaced here, so it means I found that to be a good one. Note that that has the same number of parameters as AR2, but look at the chi-square. So much better. So same degrees of freedom, but 43 instead of 456. So on the one hand, you can say that this model may be, AR2 model may be acceptable because of large sample size and the RMSEA being okay. But if you have a competing model, you can really see, with the same number of parameters, you can really see that you haven't looked at your data thoroughly enough if you stop at the AR2. The ARMA model, certainly for the same number of parameters, is much better. And if you go then further down, the dynamic random intercept models don't get that great of chi-square. Well, the AR2 does maybe, but the dynamic RI-ARMA model, when I say 1-1, that means autoregression of order 1 and moving average of order 1. 3247, that looks like a good fit. But of course you have to get up to 43 parameters, whereas you got a just as good of a fit with only 41 parameters here using the ARMA 11 model. And we're going to take a look at that model. Trying to include autoregression order 2, which works so well in the AR2 model, gives you no solutions, just too many parameters for that. The RI-AR1 model, which is the basis for the RI-CLPM model, doesn't do too well here with chi-square, but it's all right by RMSEA. But we have already seen that we get a better model if we go to ARMA. True, we have to add more parameters, we go from 33 to 41, but still I would tend to choose that, the model 3 instead of model 8. Adding a second order autoregression gives you too complex of a model. When you have that second order autoregression in these more complex models, you easily overtax the optimization because of all the missing data in these in this particular application. And then finally you have the ARMA model, which gets a good chi-square and a good RMSEA, 42 parameters and 3340. It has one more parameter than the ARMA model, and similar degrees of freedom, similar chi-square, similar p-value. So model 3 and model 10 are competitors here, but let's see which one is actually looking better in terms of the Mplus runs. So let's take a look at that. So here we have output for the ARMA 11 run, and so that is first order autoregression, and then the moving average model where we start at the third time point, because otherwise Z2 on Z1 hat would be the same as Z2 on Z1, because they are not dependent variables. Again, we add Z1 to get the likelihood in the same metric. Anyway, so this model then, 50 starting values, 49 did not converge. So you may want to use 100 starts equals 100 here, but at least those two show replication of the best log likelihood. This is in the scale of the log likelihood, taking the scaling correction factor into account. Now we can take a look at the estimates here, and you see that the moving average parameters are negative indeed. So a high residual at a previous time point tends to give a lower value of the outcome at the next time point. So that's often seen in data, and that's the feature that makes the decay of the correlations across time be slower than for the regular AR model. So now let's take a look finally then at the model for RI-ARMA, which seemed promising, good chi-square, and we use 100 starts here in addition to the coverage equals 0. 100 starts, and we look then at quite a few relatively close likelihood values, which means that the likelihood, again, cannot distinguish very well between different kinds of solutions. That says you don't have enough data, don't have enough information in the data to determine all of the model parameters. But anyway, the best solution is replicated, but we get this message. Standard errors are not trustworthy due to non-positive definite first-order derivative matrix. And that's the matrix that's used for standard errors when you use the so-called MLF, as in Frank estimator. So you have a very low condition number, which says that the model is teetering on not being identified. And FT hat, let's see, what do we have here? All of them are positive, the variances, but nevertheless, it's not quite a trustworthy solution. So let's take a look at the actually running it by MLF. This is an interesting trick that Tiemer taught me, that you run it with the MLF estimator, and then that low condition number gets reflected in the standard errors. So you see then standard errors here being quite large, not for all parameters, but down here, look at 48 for F6 on F5 hat, the MA moving average component. Same thing for F7, for F8 and F9. Those large standard errors is an indication that you get, may have when you have an infinite standard error, it means the model is not identified. This one is on its way to becoming not identified. So not a great model after all. So in this case, we probably would choose model 3, ARMA 11, with its 41 parameters. So that's neither, it doesn't have a random intercept component, and it seems to be a simple model that seems to be better for these data. I would say though that if you had t equal 11 with everybody or many people or most people having all 11 time points, I would bet that the model 10 ARMA model would win and would be the best model. But here, thanks to so much missing data, we have to settle for a simpler model than that.